Hi guys, hope you're having a good week. Here is your lesson on section 9.2, which is conservation of momentum. I couldn't get the video to play in Classroom, so I'm going to go ahead and show it here.
You saw how a force applied during a time interval changes the momentum of a baseball. According to Newton's third law of motion, forces are the result of interactions between two objects. The force of a bat on a ball is accompanied by an equal and opposite force of the ball on the bat. Does the momentum of the bat therefore also change? Let's consider the collision of two balls. During the collision, each one briefly exerts a force on the other. Despite the differences in sizes and velocities of the balls, the forces that they exert on each other are equal and opposite, according to Newton's third law of motion. These forces are represented by the equation shown here. How do the impulses imparted by both balls compare? Because the time intervals over which the forces are exerted are the same, the impulses must be equal in magnitude, but opposite in direction. How did the momenta of the balls change as a result of the collision? According to the impulse momentum theorem, the change in momentum is equal to the impulse. Let's compare the changes in the momenta of the two balls. Because the time interval over which the forces were exerted is the same, the impulses are equal in magnitude, but opposite in direction. Substituting impulses with the change in momentum for both balls, we arrive at the equation shown here. This equation states that the sum of the momenta of the balls is the same before and after the collision. That is, the momentum gained by one ball is equal to the momentum lost by the other. If the system is defined as the two balls, the momentum of the system is constant, and therefore, momentum is conserved for the system.
Okay, so that had a lot of information in it, and you can go back and watch it later if you need to, but we're going to go over some of the stuff that is important in there, but I thought that it would be a good preview for you. Okay, so when we talk about momentum, first of all, we have to remember that momentum needs to be in a closed, isolated system. Those are the two conditions in which momentum can be conserved. So the two conditions are, first of all, it has to be a closed system. Well, what's a closed system? A closed system is when no balls or objects are lost or gained, meaning I can't gain or lose mass in a system. So if I have a collision between objects, it's a closed system as long as we're not adding or taking away anything to that system that we're talking about. So as long as I don't add balls or take away balls, it's a closed system. So that's the first condition. The second condition, it needs to be isolated. Isolated means there's no external forces on this system. The net external force is zero. There's nothing else adding a force except what's inside of that. The balls can collide, but as long as they don't collide with something outside of that, then it's okay. It can be conserved. So we don't need it to be hitting a wall. We don't need it to be hitting something else that we're not including in our mass of our system. So those are the first two things that we need to remember. Something to think about, though, you don't have to necessarily write this down, but something to think about, as always, this isn't completely always true because Earth isn't absolutely isolated. There's always surroundings, there's always things around us that are going to take place, like friction or air resistance. But as in most of our other problems, we're going to ignore that. So we're going to ignore friction. We're going to ignore some of those small things like air resistance. We won't ignore if it hits a wall or something, though. Systems, when they collide, can contain objects, and they can, in a collision, they can stick together or they can come apart. So think about the balls in bocce ball. They can collide and they can come apart. Or when you guys did your sticky lab, those cars stuck together. That's okay. They can move apart together as one. or they can start stuck together and they can recoil or bounce off of each other. So what we're going to focus on in this section is the law of conservation of momentum. Basically, like any of law of conservation, it tells us that momentum in a closed, isolated system does not change. Remember, most laws of conservation tell us that things cannot be created or destroyed. So we're not going to create any more momentum, and we're not going to take away any momentum. So therefore, they have to be equal before and after the collision. This is basically an application of Newton's third law. Remember, Newton's third law is the equal and opposite one. For every action, there is an equal and opposite reaction. Okay? So if we go back and talk about forces, think about a baseball and a bat. The force on the bat of the ball has to be equal and opposite of the force of the ball on the bat. Well, we're going to look at how the momentum changes in that. Basically, it's going to apply Newton's third law, and they talked about it in the video, but we can kind of break it down and just make it a little simpler. The momentum of the system before the collision has to be equal to the momentum of the system after, because of the law of conservation of momentum. If you want to look in your book, they kind of walk through that a little bit more and talk about how that happens. But for our case, we can just simplify it, say the law of conservation of momentum, I can't create it, I can't destroy it, so it has to be equal before and after. Here's the equation for it. Momentum, remember, is given the symbol P. So the momentum of, say, object A initial plus the momentum of object B initial, I'm going to add up both of my initial velocities. The momentum before has to equal the momentum after or final. So the momentum of A final plus the momentum of B final. And I can add on however many objects I need. I can have C and D and F, but all the momentum before has to equal all the momentum after. All right, so your first example problem, this one is actually in your book on page 246 if you want to look at it, but I can kind of walk you through it a little bit. Remember, as in all things, we want to draw a picture first and show how this works. Identify what it is that we're talking about. So I have a car, where's my pen? A 1875 kilogram car. Oh, this isn't working very good. Is going 23 meters per second. You're going to have to bear with me. Drawing with a mouse isn't very good. It rear ends, so it hits a 1,025 kilogram car going in the same direction at 17 meters per second. Now, why does it tell you it's on ice? Well, so that we don't have any friction and we can ignore it and we can say it's closed and isolated. Now, this is all before. After, they stick together. So if they're sticking together, they're going to have the same velocity. So I'm going to have A and B together, but one V final. So how fast are the cars moving after the collision? Okay, so I would have my M1, momentum is MV, okay, MVI of A, this first one, plus MVI of B is going to equal M plus M of A plus M of B times my V final. Okay, because these two have to be added together and they're going to have one velocity. Okay. Work that out, check your answer, look at the page if you need to, and I left my notes for Mr. Panner, but I think you can be able to do it. Okay. All right, the next thing, or actually, I want you to look at the practice problems. Okay, the practice problems are there. My notes are for Mr. Panner. You can work them on the board. Or did you guys know that some of the answers to the practice problems are worked in the back of the book for you? So you can look at some of them. A couple of them are in the back of the book, so you can look at those. All right, the next thing is just a specific example of conservation of momentum, and that is recoil. Recoil is, when we talk about recoil, the first thing that most people think about is like a gun. When you think about recoil, you're shooting, you are both stopped. You don't have any momentum, the bullet and the gun don't have any momentum, but they're going to fire off. One's going to fire forward and one might push you back. So you're going to be going opposite, one's going to be forward, and you have to add up to the same thing, which is basically 0. You both started at 0. So when you're doing recoil, it's important to first of all define the system carefully. So for example, the momentum of the baseball changes when the external force of the bat is exerted on it. The baseball is therefore not an isolated system, but we can make it an isolated system if we look at the two, if we combine those things. An easier way is to look at the total momentum of two colliding balls within an isolated system. It does not change because all the forces between the system are equal. So first of all, you need to make sure that they're within the system. You need to identify your system carefully. All right, think about this picture here. We have two people on ice skates, and they're on a smooth surface. They're starting at rest, so they're both stopped, one behind the other. This person, skater C, gives skater D a push. You can get out the little pink carts over there on the shelf and try it if you want. What's going to happen? Well, if you look at the picture, C is going to go one way and D is going to go the other. Could we figure out their velocities? Yeah, but what do we need to know? We have to know their mass. Okay? If we know their mass, then yes, it's very easy to figure out their velocities, just like the equations that we found before. Okay? And I'll show you how to do that. After they clash with each other, they're basically colliding. They're pushing off of each other. They've had contact. Both skaters are moving, making it similar to an explosion. The push was an internal force, so you can use the law of conservation of momentum to find their velocities. The total momentum, though, has to be 0 because it was 0 before. They weren't moving. Since they had 0 velocity before, it has to be 0 after. So, same thing, momentum before has to be equal to the momentum after, but since the momentum before is 0, these two have to add to 0, which basically mean one needs to be positive and one needs to be negative. Okay, M of C times VC final equals M of D negative M of D VD. Remember your coordinate system. Don't need to write this down, it's okay. Velocities, though, depend on mass. If the less massive one will go farther because they're going to have a greater velocity. They had less mass. You can demonstrate that. You know that. We saw it with the bocce balls. Okay. You guys can come back and later you can watch this video. It's a 6-minute Khan Academy math tutorial. It shows you how to work that. So I'm going to run out of time on this one. I'm probably going to have to make another video. Okay. So this one you can come back and watch that later for practice. All right, something to think about, don't write this down, but when you're talking about space, this is kind of the same thing. How does a rocket in space change its velocity? Well, the rocket carries fuel and oxidizer. When the fuel and oxidizer combines in the rocket motor, the hot gases are they leave, okay? They're expelled. Is this closed and isolated? Yeah. It obeys the conservation of momentum and Newton's third law because they were originally all part of the rocket. Okay, so we're not adding any mass, we're not adding any collisions. Okay, but there is new technology, and I'll let you read this stuff later on or on Classroom. Okay. All right, I'm going to have to stop there.